called the birthday paradox. Birthday paradox. All right, so the question is how many people should be in a room so there's a 50-50 chance, equal probability, that two people have the same birthday. We'll assume that there are k people in the room, and we're going to number the people 1 to k. 1, 2, 3, k. Okay, so we'll also assume that there are going to be 365 days in a year. Now that's not really true because there's really 366, but we only get the 366th day every 4 years. Called a leap year, right? Anybody born on February 29th? If you are, you have to leave the room. Okay. So we're going to basically assume that the common birthday is some day, R. So you know the 1 through 365. So January 1st would be 1, January 2nd would be 2, January 31st would be 31, February 1st would be 32, like that, right? And then December 31st would be 365. You get the idea, right? So R would be one of those days, and that's the common day. So we're going to say B sub I is the birthday of some person I, because we're going to look at two people. And you can count the number of people in this room for me quietly. Okay, so basically the birthday of person I is BI. And the birthday of person J is BJ. So if R is a day that we're looking for the commonality, we're going to look at the probability that BI is equal to R as well as BJ is equal to R. That make sense? Now, because the probability that BI is equal to R and BJ is equal to R also will equal to the probability that BI is equal to R times the probability that BJ is equal to R. And that's going to be 1 over n squared, where n is the number of days in a year, which is 365. Does that make sense? Does that make sense? Yeah. Okay, so what would that probability be? This is not n2, this is supposed to be n squared, right? So what would that probability say? What is this number? 1 over what?
365.
1 over 365 squared, which is a very small number, right? Very small number. So, but basically, what we have to understand is that the probability that any two people have the same birthday, the probability, if all days are equally likely, the probability is not 1 over 365 squared, the probability is really 1 over 365. Right? Because if I was born on some day, how many days do I have to choose from? 365. So all you have to do is match my particular day. So if I start with me, then my probability of matching is 1 out of 365 for every single person, assuming they're randomly distributed. If you start, what's your name?
Tejas. T-E-J-S.
T-E-J-S?
Yeah.
T-E-J-S?
Yes.
How do you say it?
Tejas.
Tejas. Tejas. If Tejas was born on a different day than me, maybe, probably. What's the probability that he was born on a different day? What's the probability that he was born on a different day than me, Tejas?
1 and 365.
No. The probability that he was born on a different day is 364 out of 365. Which is more than 99%. Right? Which, hopefully that's the case. So therefore, the probability that two people have the same birthday is not it's not the same as the probability that they both are born on a given day. It's the probability that they're born on the same day, whatever that day may be. So therefore, since R is going to range from 1 to n, we'll let R go from 1 to n, and then we're going to sum this probability of 1 over n squared, and that's going to be equal to 1 over n, and that's the 1 over 365. So the probability that people have the same birthday is actually 1 out of 365. Now, how many people do we have in this room?
21.
21 people. Did you count me? Just 21 people? Did you make any mistakes? All right. So, the probability that at least two people out of k people have the same birthday is equal to 1 minus the probability that all the people have different birthday. Because if all the people have a different birthday, that means nobody shares the same birthday. And if the probability of that is, for example, 5%, then 1 minus 5% is the probability that it is not true that everybody has a unique birthday. That means at least 2 people must have the same birthday. Maybe 1 pair, maybe 2 pairs, maybe 3 people have the same day, but it's not unique for everybody. So the probability that at least 2 people have the same birthday is 1 minus. So what we can do is compute 1 minus the probability, and now we have another person. So that's how many? 22. I don't know if it's worth it. Maybe it is. Okay. So all k people have the. So we're going to try to calculate that. So basically, we're going to define some events. So this is some basic probability we're going to look at. Let's see if I can make it a little bit bigger. Nice. So we'll define something called events. And events are when certain things are occurring. So events have a probability. AI will be the event that person I's birthday is different from person J. So AI is the event that person I is different from person J, where J is less than I. Okay? So for example, A10 is the probability that person I has a different birthday from people, which ones? A10 is the probability that person 10 has a different birthday from whom?
Plus 9.
Persons
1 to
J, which is less than,
I.
which is less than
10.
10. So how many other people?
1 to
9.
9.
So basic, okay, you understand that. So now, BK, so you understand what is AI? BK is the probability that all K birthdays are distinct. So BK is equal to, what is this over here? Intersection of the events 1 through K, and this A1 is the probability that person 1 has a unique birthday, which is guaranteed. Intersect A2, which means that A2 is different than A1. Intersect A3, which means A3 is different than A1 and 2. Dot, dot, dot. Intersect AK, which is the probability that AK is different than than 1 through K minus 1. Okay? So PK is the probability that all K birthdays are distinct. So the probability that all K birthdays are distinct is the probability that all K minus 1 birthdays are distinct times the probability that the kth person is different than all the other people, given that all the people at BK minus 1 are different than the one before BK minus 1. What kind of probability is this? Anybody know? When we have this line. Probability of AK given BK minus 1. That's called a conditional probability. Conditional probability can change the probability sometimes, right? What is the probability that somebody scores, let's say, higher than 110 on an IQ test? Well, let's say the probability of that is 40%. But what's the probability that a person scores more than 110, given that they're an engineering student at UB? That probability is going to go what? It's going to increase in most cases. It's going to increase because you're smarter than the general population. So okay, what's the probability somebody's going to score more than 110, given that they are 7 years old or younger? It's going to decrease. Okay. So conditional probability can change because what we're doing is we're saying the probability that person AK is different from all the people before, given that all the people up to K minus 1 have distinct birthdays. So we have to have this, because this just says that AK is different than anybody before, but this says, but you're also assuming or giving the fact that all the K minus 1 people before are unique. So the probability of A1, that person in 1 is unique, is the probability that all one person have a unique birthday. That's certain, because one person has a unique birthday, there's nobody else to have a common birthday with. Okay? So probability bk is not equal to bi as I goes from 1 to k. This expands the probability and continues like this, and we have basically, whoops, sorry about that. We have the formula of 1, and then we have n minus 1 over n. Let's think about it. The probability that I have a unique birthday as the first person is certain, 1, right? Now, if n is 365, the probability that the next person, 364 over 365, and the next person, now why is it going down by 1? Again, because now this person is unique, this person is unique, so in order for this person to be unique, you cannot match these 2 days, and 2 days removed from 365 is 363, 362, etc., 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 and then we have n minus k plus 1. So how much did I subtract here? So this is going to be n minus 0, n minus 1, n minus 2, n minus 3, and this is n minus
K minus
k minus 1. So how many terms do I have here?
K.
K minus 0, so here minus 0, minus 1, minus 2, minus 3, minus k minus 1. So from 0 to k minus 1 is?
K.
So this is k. This is all k. So you see the probabilities? That's what we're talking about. So we can rewrite this n minus 1 over n is nothing more than n over n minus 1 over n, right? N minus 2 over n is n over n, which is 1, minus 2 over n, etc., etc., etc. And we can also make an observation. Now, you know what happens here when you have 1 minus 1 over n. We know that e to the x is greater than 1 plus x. So we can let x equal to negative 1 over n, which gives us 1 plus negative 1 over n. So then we have e to the minus 1 over n, or e to the x, is going to be 1 minus 1 over n, and e to the minus 2 over n is going to be 1 minus 2 over n, etc. And so therefore the probability is going to be approximated rather than multiplying these, which is very complicated because it gets a very large product. Now we have a product of these values which are going to be bigger. So if they are greater than or equal to, then we know our probability is going to be less than or equal to when we use the bigger terms to multiply. So then we're going to use this, multiply this, by all of them, all the way up to here. And multiplying them, when you multiply the same base to different powers, all you have to do is add the powers. So therefore, it's going to be e to the power of the summation from 1 to k minus 1 of 1 over n. So therefore, this is simply the summation of all the exponents. And of course, we have a sum for that. So that's going to be minus k times k minus 1 divided by 2 over n, which is less than or equal to 1/2. Okay? So the probability of bk is going to be less than or equal to 1/2. That's what we want. So so now we're going to use that exponent. When the exponent is less than natural log of 1/2, we get natural log of 1. This is the law of logs, right? ln1 minus ln2, but ln1 is just 0, so it's going to be minus ln2. Multiplying both sides by negative 2n gives us k times k minus 1 is greater than 2n times the log of 2. So now what we want to do is we want to solve the quadratic inequality for k. And k is going to be our value of the number of people. So that we have the probability, we want the probability to be, we want to have this value to be less than 1/2. We made that 1/2. Less than or equal to 1/2. So at this point we have basically a quadratic inequality, which is just like a quadratic equation. But we solve it with ranges of values rather than particular two values. And so what happens in this case, the solution becomes k is greater than 23. So this tells us that if we have 23 people or more, the probability of two people having the same birthday is approaching about 50%. Which is kind of surprising, considering the fact that the chance of me and my favorite GA over here having the same birthday is only 1 out of 365. And 1 out of 100 is 1%, so 1 out of 300 is 1/3%. 0.0033333333, and 1 out of 365 is going to be even less than that. But yet we get 23 people, and there's a chance of 50%. So how many people do we have in this room? You're going to count again?
22.
24.
You have 24 people? So really, statistically speaking, we have about a 50-50 chance that two people have the same birthday. 23 people. What's 23 divided by 365? The answer is we don't know. But we do know that 23 out of 230 is 0.1. Right? 23 out of 460 is 0.05. So it's between those two values. Okay? So we don't have a lot of representation for all the days, but yet there's a 50% chance two of us are going to have the same birthday. And that's kind of unusual. So you want to play a game, find out if we do have the same birthday? Yeah, you think it could be exciting? Now, again, if we win, we're happy. If we lose, we understand that probability is a funny thing. So what I'm going to ask you to do is, now most of you probably remember your own birthdays, right? You know, if you're married, you might forget your husband's or your wife's birthday, but you usually remember your own birthday. So what I want you to do is I want you to write down on a piece of paper the birthday of your mother, who is the most important person in the world to you. Of course, your father is important too, but really your mother is the most important one. All right, so write down the birthday. Now, I don't need the year. I don't need the year. We don't care about the year because the year is just another variable, but we just are interested in the day. All right, so let's see if we can, so do we have 24 people? We do? So that, it's just interesting. So you said we have 24 people, right? So let's see, so 24 people. So very interesting. So with 24 people here, we only have 2.6%. No.
6%.
A quarter of a percent. We have about a quarter of a percent of the possible birthdays. Is that a lot or a little? It's not that much, right?
6.5.
Because 1% would be what? 3.36 or something like that. 3.6%. All right.
5%.
So we're going to, can you guys see this over here? Is that visible?
Mm-hmm.
Yes or no?
Yes.
All right, so we'll see what happens. All right, so listen carefully. Everybody got their mother's name? Not their name, but their birthday. Okay, so right now we have 24 people, right? So now, if we wanted to find out the probability to go up to 75%, what would we do different from this formula? How do we find a different value for k? Would k be higher or lower for 75%? Number of people. Would we need a higher number of people to get 75% likelihood? Okay, so where would we make the difference in our... Remember how we said less than or equal to 1/2? So we'd say less than or equal to 0.75, and we'd get a different value for k, different quadratic inequality. Okay, so how many people, first of all, how many people have birthdays in January? Raise your hand if you have a January birthday. Raise your hand. Okay, so I can tell right away that you are not going to have anybody matching your birthday. And what day is it?
22nd January.
22nd. Okay, so you don't have any chances. So I'm going to cross you off right away. Because nobody else is January, right? But I'm not going to cross it off. Not yet. I'll cross you off later if I have to. Okay, February, raise your hand. February. February. Wow. What's the number?
28.
28th. March. March, 2 people? What's your number? 25. What's your number? 11. Okay. April. April.
29.
29th. Correct. And what's yours?
22nd.
22nd. May.
This is the birthdays of our mothers, right?
No. This is just you. Are you playing the game correctly? Are you May?
Yep.
What's your number? Anybody else in May? Just one May? What's your number?
22.
22. Okay. June. Wow. We have very unpopular people. Okay. June. Everybody going to be born in December. What's your number?
25th.
Okay. July. July. 2 people. What's your number?
20th.
And yours?
7th.
Okay. August. 1 person.
11th.
September. 1 person.
12.
October. Wow! October is a very popular. Okay. Raise your hand and hold your hand up if you're October. Go ahead.
First.
Wow. You just made it.
15.
15. You're almost.
Half.
8.
Huh?
8.
8th. And you are?
14.
14th. Look at that. 4 people, but we don't have a match. You guys are a bad example. Bad example. Okay. November. November. We have 2 people for November. What's your? Yeah, you.
8.
8. And what's yours?
12.
Louder.
12.
12. Okay, in December, last chance we have.
Chris.
1 person. What's the number?
11.
11. So let's see. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How can we have 19 people? What is wrong with you people? Okay, who did not get selected yet?
Isn't there anyone?
Are you guys
Said
listening?
October 15th.
What's going on?
You were asking mother's birthday.
Yeah, even we thought that you were asking mother's birthday, so we started with that only.
Come on, are you serious? Mothers you just write down mother. Mothers are for later. Okay, so how many people gave me mother's birthdays? Okay, raise your hand if you give me mother's birthdays. Okay, I want to know all of you, because now, okay, so I have 1, 2, so I'm going to go.
Just start.
Who didn't give me anything? Okay, who didn't give me anything yet?
Karan,
And you are missing too.
You gave me something.
I gave you that.
Okay, if you didn't give me anything, what, I'm missing something?
You are missing.
You don't added yours first.
My birthday?
Yeah.
That goes last. That goes last, in case you have a present for me. Okay, that goes last. Okay, so who did not? So base of 19, so I'm expecting 20, 21. I have 4 people who didn't give me anything. Am I right? Right? Who are the 4 people who didn't give me anything yet? So you didn't give me anything yet? What's your birthday?
December.
December what?
27.
27. Okay, who's the next person to give me anything?
January.
January. Okay.
Next, who didn't give me anything? You didn't give me anything or you gave me something?
No, nothing.
Didn't you give me your mother or something? Or
No, no,
you didn't give me anything?
nothing.
Nothing. What's your birthday?
January 4th.
4th. Okay, and then Conveer?
March 1st.
March 1st. Because everybody gave something, okay? All right. Okay, so now we have 4, so that should be 23 people. So we have 23 people. That's exactly the right number, so our probability is 50-50. So do you think we should go a lot higher to match it? So now let's find out. So we're going to add 1 person at a time. So who has a mother? Raise your hand.
Everybody. Yes.
Anybody have a mother here? Okay. Anybody like their mother?
Everyone.
Love their mother?
Feel.
Anybody afraid of their mother? Good. Who are you afraid of more, mother or father? Father more? Mother more. Because mother can hurt you, and if she cannot hurt you, she can tell your father. So mother has double power. Okay, so let's find out. Okay, so we're gonna so who didn't? So I want some. So who gave me only mothers? Who gave me the mothers before? Okay, so now I want to have your birthday.
August 1st.
August 1st. Okay, oh, if you gave me a mother, raise your hand. What's your birthday?
29 December.
What's your birthday?
28 January.
Huh?
28 January.
January 28th.
So we have, what, 3 people? We just had 3 people. Did you give me your birthday yet? Mother's birthday?
Yeah, I gave you.
The mother's, right? What's your birthday?
July 12th.
July 12th. Oh, 12 is here. It's 4. And who else gave me a mother? So give me yours.
April 9th.
April 9th. And you gave me a mother?
January 12th. Yeah.
January 12th? And who else gave me a mother?
17th September.
September 17th. Wow. And
16th May.
May 16th.
March. That's March.
Okay, everybody else, no more mothers, right? Okay. So we have at least 6 people, but we're at 29.
Professor Abad, she gave Jan 22 as well. That's your birthday?
So so that you have to scratch out. 22nd January I gave, which was my mother's birthday.
That's okay.
That's okay.
But then you gave me yours too.
Yeah.
Which
I
was?
gave yours too. 16th May. Which
What
you
is
added the last.
That's okay. We have some mothers added on.
You have March 1st as well, right?
No. Just to put.
She knows her mother's birthday.
His was March.
All right. So now, let's see. So let's see who did not give me any mother's birthdays yet. So when is your mother's birthday?
November 12th.
November 12th. Okay, and look at that.
Oh.
All right. So it took us 30 people. 30 people. So we're a little bit above. Usually it usually comes up a little quicker. But it's interesting. So with 30 people, we found that we have 2 people having the same birthday, even though 30 out of 365 is still less than 1%, less than 10%. So about 8 to 9% of the days, and we have 2 people on the same birthday. All right. I would have added myself earlier, but I don't match anybody's birthday. But there is one person who's only 1 day away. Yeah. The probability of you guessing of this one is going to be 1 out of 30. All right. So now let's take a look. So now that we're having some fun with some probability, we are going to use a different approach to try to find the likelihood, and we're going to use something just a binary variable IR. Indicator random variable IRV, indicator random variable. So Xij, we'll say Xij is equal to 1 if person I and person j have the same birthday. Xij will be 1 if people have the same birthday. So if you're person 5 and you're person 7, X57 is 1 if you have the same birthday. It's 0 if you don't. So it's a binary variable, 1 or 0. So the expected value, an expected value is not whether it's true or not, it's what we expect. So for example, if I am a random person and I take another random person, then and I am I and they are j, Xij is 0 or 1. But the expectation is that it's going to be what? What's the probability? Expectation is the same as the probability of us having the same birthday. So expected value is what? 1 out of 365. That would be the expected value. So the expected value of Xij is the probability that the person I and j have the same birthday is 1 over n, which is very similar to what we did before. So therefore what we're going to do is we're going to let x be the summation of all the Xij's. So we're going to let x equal the sum as I varies from 1 to k, everybody, and as j varies from I plus 1 to k. Do you see what I'm doing? Why am I using j is equal to I plus 1 to k?
Second person.
So that's the second person. So if person I is 1, then j will go from 2 to k. When I is equal to 10, then j will go from 11 to k. Why am I doing that? So when j is
First person.
10, I'm going from 11 to k. So that means 10 cannot be matched up with 9, 8, 7, 5, 4, 3, 2, 1, because when I was 1, I already would have matched it with 2, 3, 4, 5, 6, 7, 8, 9. So I'm making sure that I don't double count, because xij and xji would have the same value. So I'm making sure that every xij is a unique pair of people. Remember, xij and xji are the same, because I just switched the people, so it's either 0 or 1. So this allows me not to have any two people pair up more than once. Okay, so for example, for me, I would say if I am x1, then this would be x12, x13, x14, x15. But when it's time for her, she would be x23, x24. She wouldn't go x21, because I already did x12. Get it? So this allows me to have unique pairs selected. So I need to find the summation. So this is the summation of x, and x is the sum of all the xij's. So therefore, we want to know what is the expected value of this double summation. And the expected value of this double summation is the summation of the expected values of xij, which is equal to k choose 2, 1 over n. Now, do you know why I'm using k choose 2? Because, basically, k choose 2 is the number of pairs of two people from k I can select. So, for example, when k is equal to 30, 30 choose 2, binomial coefficient 30 over 2 is 30 factorial over 2 factorial times 28 factorial, which is going to be 30 times 29 over 2. That's how many different pairs we have. So basically, this, if I said the sum I to k, I plus 1 to k of I, that would be k choose 2. That is the same value. So it's going to be k choose 2 times 1 over n, because expected value of every xij is 1 over n. So that's why this is k choose 2, 1 over n. And of course, k choose 2 is going to be k factorial, 2 factorial, and then k minus 2 factorial times 1 over n. And we get k times k minus 1 over 2n. Okay, everybody understand how I got that? Good. So we need to solve when k times k minus 1 is greater than 2n. The expectation is then at least 1.0. So we're looking when k times k plus 1 is greater than 2n. So again, we're going to get a quadratic inequality. K squared minus k minus 2n is greater than or equal to 0 gives you the solution for k. Must be greater than this, must be greater than this simplified, equals to this. So 365, we expect that with k is equal to 28, we expect that two people will have the same birthday at 28. Now we didn't quite hit it until what?
30.
Okay, but that wasn't so much above 28, right? If we went to 48, I would be like fainting. You'd be like, what's wrong with Professor Dichter? You know, he's just blown away by the probability that cannot happen very often. So it's going to happen only once in my lifetime. But so you can see that 28 is the actual number that we expect it to happen. It doesn't mean that it will happen at 28. It may well happen before, but it shouldn't happen much past 28. So 28 is the target. Okay? That's the average. Do we always hit the average? No. But as we start going above 28, the probability of not having it gets smaller and smaller and smaller. So there's a very good chance. What's the probability that we'll have 30 people in a room and they will all have different birthdays. How do we write that equation? We already had that before on the board, right? That would be 1 times n minus 1 over n times n minus 2 over n times n minus 3 over n times n minus 29 over n, where n is 365. That would be the exact probability, assuming that every day is equally likely for somebody to be born. Okay, any questions about that? Okay, so that's the result we got. So this is k times k minus 1 over, so we want this thing to be equal to? We want the probability to be greater than or equal to? To 1. So if this is greater than or equal to 1, then k times k minus 1 is greater than or equal to 2n. Then the expectation is at least 1.0. What if we wanted to find out when the probability is 50%? How do we solve this? When would the expectation be 50% or higher? When this ratio was what? Greater than or equal to what? 0.5, which is 1/2, right? So that would be the case where this was greater than or equal to 1/2. 1 over 2. So if we multiply by 2n, we get what? We get n on the right side, and the equation would be k times k minus 1 is greater than or equal to n. So the equation would be k squared minus k minus n is greater than or equal to 0. We get a different result. Okay. So let's look at, I'm going to look at one more problem today with probability. Okay, so let's look at all right, so we're going to look at a pretty simple problem. And we're going to look at a problem of, we're going to be hiring a assistant. So we're going to hire a new assistant. Her name may be Jackie or somebody like that, whatever her real name is. Okay, so what's going to happen is, every day we're going to be sending a candidate for an agency, we'll be sending a candidate to us every single day. And we will interview the candidate, and we must decide immediately whether to hire that person or not. If we hire the person, we have to fire the current one immediately. So everybody was going to assume is going to have a unique quality or quantity. So let's say the value, your lowest quality is 1. It's very, very bad, knows nothing. And let's say the highest quality is 1,000. So we're going to keep getting people, but we could get 500, 40, 700, 365. So we want the best person. So initially we have nobody. So we get the first person, what are we going to do? We're going to hire that person immediately. Whoever is the first person, we're going to hire them. First we'll interview them, then we'll hire them. So we're going to look at the cost of our algorithm. The cost of our algorithm to hire the best person every single time is the cost to interview person I, is CI, and the cost to hire is CH. But we're going to interview everybody. So that means that since we interview everybody and we have n people to interview, then we're going to have NCI will be the cost of interviewing all n people. But we're not going to hire all n people. We're only going to hire the people who are better than anybody we have so far. Okay. So what is the cost of this algorithmic strategy? So basically, we're going to say the best person has a quality of 0, which is very low. That's going to be just a startup value, so that we hire the first person. And then for I goes from 1 to n, we'll interview candidate I. If candidate I is better than the one we have, then I is the best, and we'll hire I, which is the best. And we'll do that for every one of the candidates from 1 to n. So we'll always interview them, but we'll only hire them if their condition is met. So we cannot decrease in this algorithm what cost? Cost of interviewing is a constant. It's going to be NCI, N times the cost of interviewing. But the cost of hiring will change. And maybe the cost of hiring is very expensive because we have to fill out paperwork, we have to do this, it takes time. So maybe that's a cost we want to minimize a little bit. So we can see that, let's determine the total cost of hiring the best candidate. If N candidates exist and M are hired, where M is less than or equal to N, then the cost is theta NCI, cost of interviewing, plus MCH, cost of hiring. We have to pay the NCI, so we'll focus on analyzing MCH. And MCH is going to vary depending upon what?
Quality.
But what is that mathematically?
Each person.
The
Yeah, but it's good. But let's say the agency will randomly pick a person to give us. So if they have, let's say, 30 people, they're going to randomly pick one every single day. Okay. So if we have 30, if they pick one sequence, if they have to do it again, they'll probably get a different sequence. So those two sequences will have different CH costs, cost of hiring, right? So what will determine the cost of hiring?
Comparison.
Okay. Think about this. What is the fewest people I would hire? When would that happen? Zero would be bad because I have to hire the first person. What would be the fewest person I hire?
At least one.
one.
Okay, when would I hire one and never anybody else?
The first
First
person
one is the best.
Okay, so if the first person is the best, I hire that person. Everybody I interview afterwards is less than that, so I will never hire again, and that minimizes my cost. But the question is, what's the probability of that sequence?
One.
Given that we have n candidates coming in at random.
1 by n.
1 over n, so it's 1 over n. So if we have 30 candidates, it's 1 over 30, which is about 3.5%. Not very likely, right? It's not very likely. When would I hire twice?
If the second person was the best. So I have to hire.
So I have to hire the first person, just like in our little algorithm when we have the MST. We always have to take the first shortest edge because it always connects two unconnected components. In this one, we have to hire the first person no matter what their skill level is, because what? Because we don't have anybody. Our skill level is 0, so the lowest skill level a person can actually have is 1, up to 1,000, so the first person is 0 initially, so we hire the first person. But if the next person is the best, that's the last time we're going to hire. Now my question to you is, given 10 people, what's the probability we hire twice? Don't be too fast. What's the probability we hire twice? Well, we know that in 10 people, the best person has to be in position 2. But who can be in position 1?
Anyone.
Anybody. So that means,
One minus.
N minus.
hold on a second. So that means this position is fixed. That means the order of position 1 and position 3 through 10 don't matter. How many ways can positions 1, 3 through 9 be? 9 factorial. So these positions can be in 9 factorial different ways as long as you freeze this one. So therefore, what's the probability going to be? So the probability of hiring twice is going to be what?
N minus 1 square. N minus 1 square.
How many possible orders can we have? 10 factorial.
8 to 9.
10 factorial. So those are all possible orders. How many orders do we have with the best person in position 2? 9 factorial. So you take the 9 factorial over 10 factorial. 9 factorial over 10 factorial. What's that going to be? 1/10. So there's a 10% chance we're going to do that. So if 10 people, what's the probability that we only hire once? 1 out of 10.
10%.
What's the probability that we hire twice? 1 out of 10. Now, how would we calculate the probability of hiring 3 times?
Same 1 out of
3 times, 3 times, 3 times. That means that the top 2 people cannot be in positions 1 and 2.
2 into 8 factorial upon
1 person. Okay, so you can see that it gets a little more complicated, right? It gets more complicated. For example, how would we know that out of 10 people that we're going to hire, when would we hire 5 people? 5 times. That means the best person has to be in position, the 5th hire. The 5th hire. Not 5th position, 5th hire. Because this gets more complicated because we can hire 5 times person 1, 2, 3, 4, and then position 10. Or position 3, 5, 7, 10. You see how it gets more complicated? So the counting of this gets very, very involved. Okay, so we want to focus on analyzing the hiring cost. So let's take a look how we would do that. So we're going to say our cost is going to be, what do we expect on the average case? So we're looking at the average cost. We understand that if we had to calculate a specific cost of hiring 5, that may be difficult to understand from the standpoint of the combinatorics of the binomial of the combinations. But let's think about the average case. What's the probability of hiring the first person? 100%. 100%. Why? Because we don't have anybody else. Okay, what's the probability of hiring the second person? I'm the second person. I want to know what's my probability of being hired. Does being second give me a better chance of being hired than being 20th?
Yes.
Yes.
Does being second give me a better probability of being hired than being third?
Yes.
Why?
1 per because the second person has a 10% probability. And
Okay, so the probability of hiring the first person is certain. We only hire the second person if they're what?
higher than
If they're better than the first person. So that means out of 2 random people, so what's the probability of them getting hired?
50%.
How about the third person?
30%.
The probability that I get hired as the third person is the probability that I'm the best out of 3. And what's the probability of being best out of 3 from a random sample? 1 out of 3. So as we go to the person further and further down, what's the probability that we'll hire the 20th person? 1 out of 20. So your probability of being hired is decreasing. It goes from 100% to 1/2, 1/3, 1/4. It's kind of like a, what does it sound like? What kind of progression? Oh!
Automatic.
Harmonic. Harmonic. Okay. So, we're going to assume that candidates coming in random order. So we know that we have a set of random n factorial possible orders or permutations. This is just showing us how we can randomize the data, so I'm not going to worry about that. So now we're going to assume the data is randomized. So we can analyze the hiring problem using IRVs, indicator random variables, which we just did in the previous problem, which is the x sub ij type of thing, okay, or x sub I. A simple technique for computing the expected value. We can have a convenient method for converting between probabilities and expectations. And we have the IRVs only taking 2 values, which is 1 and 0. So basically, we're going to say the IRV is going to be as follows. The indicator random variable for event A is 0 if the hiring does not occur, 1 if the hiring occurs. So again, it's a very simple 0, 1 case. So x sub A will be I of A, the indicator random variable of event A. So the expected value of x sub A is the probability of this event occurring or not occurring. So the expected value of x sub A is the expected value of the indicator variable of A, which is 1 times the probability of occurrence plus 0 times the probability of not occurrence. Since 0 times this is 0, so therefore the expected value of XA is just the probability of A. So now what we have is we have XI is the indicator random variable that the candidate is hired. 1 if they're hired or 0 if it's not. So therefore our X, just like before, instead of having two people IJ, XIJ, we just have XIs. So X is the sum of all the values. X1 has value 0, 1. 1 if X1 is hired. That will be 1. X2 will have the value of 0 or 1. 0 if they're not hired, 1 if they're hired, we don't know. X2, we don't know. Xn, we don't know. So we need to compute the probability that the candidate is hired. So candidate I is hired only if I is better than everybody before them, which is 1 through I minus 1. By assumption, the candidates are randomly ordered. So therefore, candidates 1 through I arrive in random order. So therefore, the probability that candidate I is the best so far is simply 1 over I. And that's what we were talking about before. The probability of the fourth person getting hired is 1 out of 4 because they have to be the best out of those 4 people. If they're not getting hired. So the probability that they're best is 1 out of 4, so that's the probability of getting hired. So 1 over I is the probability of getting hired. Okay, so as the value of your order increases, your probability of getting hired decreases. So what we want to do is we want to compute the expected value of x, which is going to be the summation of all the x sub i's. So the expected value of x will be equal to the expected value of the summation of all the x sub i's. And the expected value of an x sub I is nothing more than 1 over I for each value of I. So we will sum from 1 to n 1 over I. So we know that this sum does not have a closed form because this is 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. We might recall that this is going to be a harmonic series, and we know the harmonic series does not have a closed form, but it does have an integral that bounds it, which is what? Nobody remembers? Okay. So first we write the series, this one. Now what we're going to do is we're going to say this from 1 to n is equal to 1 plus from 2 to n. Now, why am I doing that? Anybody know? It's the same thing, right? 1 to n, 1 over, because when I is 1, it's just 1. So I just pulled out 1 out and I just started at 2. Why did I do that? Because this sequence is decreasing or increasing? It's decreasing. So therefore the upper bound has to start at the value of a minus 1. 1 lower than the lower limit. And that would be, in this case, 1. But here it would be 0. And 0 is bad. Why? Because 1 over 0 is not defined. So that's why I had to do that. Okay? So I had to basically just take that 1 out. So now therefore what I have is I have the summation from 1 to I from 2 to n is going to have an upper bound. Notice I backed up the limit because it's decreasing. So since it's decreasing immediately, I have to back up to 1. So it decreased to this value. And to make the interval just as wide, I went from 1, which is less than this, up to n. And the lower bound can start at here because it's decreasing up to n plus 1. And that's going to equal to, so that's the lower bound. The upper bound is going to equal to, this is going to be nothing more than the integral of this is going to be the natural log of n, evaluated, the natural log of x evaluated at n minus 1. So it's ln n minus ln 1, which is ln n. So that is our solution. So what does that mean? It means that if I have, for example, if I'm going to get 25 people coming in from the agency, if I have 25 people coming in and they are selected in random order, then I can expect, on average, from those 25 people, to interview or to hire about 3. So that tells me what my algorithm of hiring is expecting, assuming random data. What if the agency is playing games with us and they say, okay, we have 25 candidates, we're going to send you one every day. They might play tricks with us, like, want us to, maybe some bad ones then a good one, and some more bad ones and a better one. So we're always looking for the better one. But so if we can, so how can we make this fit our mathematical model? We could tell them, send us the 25 names, and we'll tell you the day before who we want, and we'll randomize the order. Okay? And that way, we're going to hire approximately 3 people out of 25. So LNN is the result. Okay, any questions about that? Easy? Some nice little fun probability stuff today. All right, homework assignments coming soon. You're going to get 2 more homework assignments. Keep you a little bit busy. But now you have a lot of material that you can do problems with, right? All right, see you guys.